I will begin with a word of prayer. Dear Heavenly Father, we thank you again for this class. I thank you for this time we have just to meet, study your creation. Just pray that you'd guide our thoughts today, help us to glorify you what we do, and just to understand a little bit more about the generalized Stokes theorem and how all this integration on forms works, Lord. In your name I pray, Lord Jesus. Amen. So one thing I kind of glossed over last time was why the integral in R3 of a 2 form is the surface integral. And I think that's something I can for sure do at the moment meaningfully, and it would be healthy for us to look at that. So let's do that. I'd like to show you the proof, or at least sketch the proof, of the generalized Stokes theorem, but I have not had. I'm not sure my mind is clear on how that should be shown. I mean, I know in some sense, but having a fuzzy idea and explaining to somebody else are two different things. So anyway, let's look at this to get started with. So let's consider, a vector field F on some surface which is a subset of R3. Then, of course, we can construct the flux form, right? Which is like, if we use the usual PQR notation, it's like P dy wedge dz plus Q dz wedge dx plus R dx wedge dy, all right? That's the flux form, right? And so if we also, let's say, have x is the parameterization in question here, so it's a mapping from D, which is a subset of R2, to S, which is the surface in R3. So the picture, something like, here's my parameter space, and then here's my surface, right? And my patch goes like so, right? The flux form lives up here, right? It lives on the surface, let's say. But if we want to integrate the integral of the flux form on the surface S, right, is by definition the integral of the pullback of the flux form, right, to D. All right. So, I don't feel the compunction, and not just that, I just don't think it would be right to put a differential next to this. See, because the differentials in these integrals, they're in the forms, right, as a notational kind of benchmark. I mean, this idea that we have to write a differential on the integral, it starts to fade as we get into higher forms of integration. That's one of the things that drives Dr. Skimbortis crazy, is like people making some sort of philosophical meaning of the dx in the integral as independent on its own in some sense. So surely the way I teach Calc 3 would be an offense, because I actually do try to talk about for example, today I was talking about the vector surface area element as if it had an existence independent from the integral itself, right? Like ds vector is the normal vector times du dv, basically. Or the ds is the square root of x dot squared plus y dot squared dt for, the arc length element for a parametrized curve in the plane. I think about the things that build an integral independent from the integral itself, just as a sort of a mnemonic, if you will. But that's kind of not where we're at here. All right, so let me get to the point here. So we want to calculate then, how do you actually calculate that pullback, right? What does this mean, integral of the pullback of the flux form of f, right, on D. So what's that actually look like? So here we should think of x as equal to x, y, z, right? These are all functions of the parameters u and v, right? So basically this is, by definition, the integral, say, of u comma v in D, right? And we're supposed to be, you know, well, I guess I can do it like this. It's the pullback, using properties of the pullback, right? It's the pullback of P times the pullback of dx, dy wedge dz, right? Poor planning on my part, right? Plus the pullback of Q times the pullback of the dz wedge dx, right? Plus the pullback under the patch of R times the pullback of dx wedge dy, right? But let's do, now I guess there's 6 pullbacks to talk about there. 3 of them are super easy. What's the pullback, what's the pullback of P? Well, that just means P of, that's just nothing more than P composed with X, right? And the pullback of Q is exactly Q composed with X, right? And the pullback of R is R composed with X. And that starts to be familiar to you if you think about the definition of the surface integral. You take the vector field and you compose it with the parameterization in order to calculate the surface integral, right? So that's that. That's where that's coming from. But on the other hand, if we look at the pullback of dz wedge dx, what's that look like? Well, that looks like, partial z, partial u, du, plus partial z, partial v dv, wedged with partial x, partial u, du, plus partial x, partial v dv, right? That was how this was accomplished. We plug in the parametric formulas and we take the total derivatives. That's the pullback. I mean, that is literally what we did. And so when you multiply this out, what you got? Well, you got you got your partial z, partial u, partial x, partial v, minus partial x, partial u, minus, well, however you want to write these, partial z, partial v, partial x, partial u, du, wedge dv. So in H.M. Edwards notation, this is partial z comma x, partial u comma v, okay? And a similar calculation holds for the other 2 forms, right? Like the pull form, well, that's a new one. The pullback of, oh, I guess I should have done dy wedge dz, right? It's going to be, when we work it out, it's going to be partial y, partial u, partial z, partial v, minus partial z, partial u, excuse me, minus partial, let me do it the same order here. Keep my pattern the same. Partial y, partial v, partial z, partial u, du wedge dv. Or if I use H.M. Edwards fancy schmancy notation, partial y comma z, partial u comma v, du wedge dv. And likewise, the pullback of dx wedge dy is going to work out to partial x comma y, partial u comma v, du wedge dv. Okay, so put this all together, what happens? We see that the integral of the flux form over the surface is equal to the integral, double integral, of course, over u comma v and d of what? Of p of x of u comma v times what? Times the p gets paired with the yz one, right? So that gets, you got your partial yz, partial uv, and then I've got the q, right? Next up is the q plus q of x of, whew. All right, here we go. Plus q evaluated the parameterization, partial, let's see here, with the q came packaged with the zx one. So zx uv, and then plus r of, at the parameterization, and then you got your xy one, right? All of that times du dv. Okay? But what is that? That is the same as the double integral for points in our parameterization of the vector field, you know, p, q, r, evaluated at the point, because I want to write the evaluation once, if you don't mind. That dot product with what? Well, dot product with the vector partial yz, partial uv, partial zx, partial uv, partial xy, partial uv, du dv. But this is exactly what you get if you look at the determinant of x hat, y hat, z hat of like partial x, partial u, partial y, partial u, partial z, partial u, partial x, partial v, partial y, partial v, partial z, partial v. Regretting this notation. See, because like for instance, the x hat one, it gets y, partial u, partial z, partial v, minus, you know, partial y, partial v, partial z, partial u, which if you go back to the other board is exactly what we had over here, right? That is exactly, of course, partial x, partial u cross partial x, partial v, which we should recognize as the normal vector field to the surface. So we're taking the vector field, evaluating at the parameterization, taking the dot product with the normal vector field. That is the surface integral. Assuming that this is, of course, a regular surface. So, you know, usual Calc 3 notation, double integral over s of f dot ds, which is what I claimed last class, but I haven't proved that last time. Any questions? All right, so trying to think. So it's kind of fun in this current notation to like play around and see if we can see any kind of like result, like theorems related to Stokes' theorem in view of the exterior, I mean the exterior calculus and everything we have going on here. Like we could try something like, let's see here. What if we did like the integral over a surface of omega f wedge omega g, right? That would be the, so here's just a, what do I want to call this? Example 1. Also known as just messing around. So this, of course, we talked about this. This is the flux form of what? The cross product, right? So that's just algebra so far. But then if we believe the generalized Stokes theorem, we can say, well, this is really equal to the integral over the boundary of the surface, right? Of the exterior derivative of omega f wedge omega g, right? And what's that look like? Well, that, by the product rule, the Leibniz rule, right? That's really the integral over the boundary of what? Of omega f, excuse me, my bad, d omega f, right? Wedge omega g, right? Minus omega f wedge d omega g. Which you might recognize as what? That's really the integral. Oh, my bad. Oh, I'm so sorry, Ernesto. This is total nonsense. If I'm wherever the boundary is, the differential does not belong. Okay, this is generalized Stokes theorem. I'm doing it wrong. So what I should be saying, instead of s, I should like let s be. I mean, s is fine. S is fine. But let's S be the boundary of some solid region. I've been using E for it lately. So suppose S is the boundary of a solid region E. Then this is supposed to be not boundary of S, but E. All right? And that'll make more sense because I was about to say, wait a minute, how can I integrate? This is a 3 form. What am I doing? But here it is. You got yourself a the flux form of the curl of f, right? Wedge with omega g minus the wedge, the work form wedged with the flux form of the curl of g. And well, lo and behold, what we really have, let me just get to the point here, is we have the triple integral over E, right? And this gives me the dot product of the curl of f with g minus f dot product the curl of g, right? Dx wedge, dx dy dz rather. Because I'm going back to a regular triple integral. So check it out. This triple integral is apparently equal to what? It's apparently equal to the flux over the boundary of E of what? Of the cross product of 2 vector fields f and g. So the flux of the cross product of 2 vector fields through the boundary of a surface is apparently equal to the integral of the divergence. Well, it's not divergence, right? It's what? It's the integral of the dot product of the curl of one with the other, the difference as well, right? I don't believe I cover this in Calc 3. But certainly I could. You know? I mean, the ordinary derivation of this theorem looks like what? You just do what? I would go from, if I start with the surface integral, then I use the ordinary divergence theorem, and I got the divergence of f cross g, right? And then because the divergence has that identity, that's the theorem, I think. Is that true? Is that it? I think that's it. Did we derive this before? Like the divergence of the curl, excuse me, the divergence of the cross product is the dot product of the curl like this. Did we work that one out? I think we might have worked that out the other day. Certainly could work that out. All it comes from is just, taking the derivative of the wedge product of the work forms, and in the fact that the exterior derivative of the flux form is the divergence of the vector field finding form. So, okay, anyway, yeah. So, all right, let me try to talk about orientation. So let me take a step. I'm going to take a step way back and try to start talking about the. So I know this is kind of putting the cart. I put the cart before the horse here, right? Because I've showed you the major application of the exterior calculus, but I haven't really defined the derivative. The integral of a form carefully in here yet, have I? Not really. I mean, in the sense that. We haven't really defined what we mean by an oriented surface, so that's kind of the giant. And what is a manifold with boundary? I'm not sure I quite have that in these notes. I'm trying to follow the notes in here, right? Let me think about my life here for a second, whether or not I want to get into this. So I'm belaboring the idea of covering page 251, where I talk about orientations and submanifolds. Probably should. So yeah, basically these 3 pages are a careful lead up to the proper definition. So let's just take our medicine and do it. So I'm backtracking a bit here. I want to talk about orientations and submanifolds. All right. So a K-manifold M is an oriented manifold if all its coordinates on M are consistently oriented. Let's say all its charts on M are consistently oriented. Now you wonder, what on earth does consistently oriented mean, right? Begs the question, obviously. So if we make a choice and we say phi naught is right-handed, all right, so if we declare, a patch, so I guess I'm using patches here. Of course, the inverse of this is the chart, right? So phi naught, which goes u naught to v naught, is right-handed. Okay. Then any overlapping patch phi 1 So what does it mean, overlapping? That would mean that like V1 intersect V0 is not empty, right? Yeah. Then this one is said to be right-handed. Right-handed. If the determinant of the transition function from 0 to 1 is greater than 0. Now, if the determinant of the transition function is negative, else the determinant of the transition function would be negative, and that would imply that phi1 is left-handed. Left-handed patch, or if you want to talk about the inverse, we could say left-handed patch, we could say left-handed coordinate system, we could say left-handed chart. Okay, we allow ourselves the flexibility of talking about one or the other. Now, you probably, like me, have forgotten what theta 0, 1 means, right? Yeah. Okay, so that's fine. Let's talk about it. So here's my M, right? And here is maybe V0, and here is V1. And so this would be my phi0, over here would be my phi1, down here, here's your U0, over here, your U1. So the thetas are my notation for the transition functions. So like, let's see here. So if I go like that, down here I could do phi1 inverse composed with phi0, for example. Phi0 and then phi1 inverse back down, or if you prefer, x1 composed with x0 inverse, if we want to talk about the charts. So the theta, and I've forgotten my notation, but I think this is it. Theta 0, 1, going from 0 to 1 is equal to x1 composed with x0 inverse if I'm using the charts. Now that is, by assumption, a smooth map on our K, right? Because these are our K, right? So this is smooth map on some open on some open subset of our K. So the that's not quite right. I shouldn't just say the determinant of. Do I just say theta 0? Oh, no, I don't. I don't. My notes doesn't just say that. What does my notes have? I have the derivative of that. All right. And what does that mean? What does that mean here? I'm talking about the differential of the transition map. So what this really is, just to be more explicit, is it's the determinant of the Jacobian of the this guy here, the transition map. All right, and all right.
But in many dimensions, what do we mean by right-handed?
This is the definition.
But aren't we saying if we declare phi0 to be right-handed, then phi1 is right-handed? But when we declare phi0 to be right-handed, what do we mean?
We're saying it's right-handed. We're declaring that to be a positively oriented chart. So any other chart that has the same orientation as it must have the Jacobian matrix must have positive determinant for it also to be right-handed. But that's a choice. You're right, that's a choice. See, I picked my first chart. I can either declare it to be right-handed, which is just synonymous with positively oriented, or I could say it's left-handed. There's a choice.
I guess what I meant that we only have two options.
Yeah.
Even though we have k dimensions.
Even though we have k dimensions, there's still, let's see here how to say this. Let me see if my notes help here. There are definitely,
We have two orientations.
there are only two orientations for a manifold in k dimensions. Yeah, even though it's k-dimensional, it's not like, well, even for calculus 3, think about this. There's a curve, there's its reversal. There's a surface. You can either orient it up or down, but the normal either goes up or down, even though it's two-dimensional. It's not like there's more of like a spectrum of orientations for a surface. Either a curve or its reversal. Surface oriented up or oriented down. The volume, you can either orient the volume, we don't think about this as much, but a volume is positively oriented if it's oh man, how to say it? Well, the positively oriented volume, the boundary of the positively oriented volume is a surface with normals that are pointing out of the volume, or if there's a hole inside into the interior of the volume, right? So like that's how you pick up on it's harder for me to visualize what is an orientation of a volume. But, well, let me just talk about that for a second here. Example 2. You know, my volume could be something like this, you know. 3 x, y, z in R4, right? I mean, that's basically it. I guess I could just say 3x, y, z such that x, y, z are real. There we go. All right. So that's a three-dimensional manifold that's sitting inside R4. I could orient it. So to orient the manifold is, and this is what I'm getting to, I haven't quite got to it yet, but if you can give for a k, what I'm trying to explain, and I'm taking my sweet time to get to it, but is to orient the manifold, one way to say it would be that, like I'm doing here, I pick a chart and then I say it's right-handed, and then I say, well, there's an atlas of consistently oriented charts, right? But we'll be able to argue that that is equivalent to saying, oh, well, here is a K-form that is defined on your manifold, a non-vanishing K-form. So like on this one, this E, from that perspective, which I haven't gotten to, I'm jumping ahead, I'm sorry again. You know, I could orient E, I could let like one volume, let's say volume 1 form on E, I could use dx wedge dy wedge dz. There you go, that's a non-vanishing 3 form defined on E. I could orient E with that. But I could also orient it with this. Right? And that would be minus the other orientation. So basically the thing is, you can, if you're looking at a k-dimensional, if you're looking at a k-dimensional manifold, at every point you have differentials, right? Like, so like So like here, basically I've got something like, dx1 wedge dx2 wedge wedge dxk. I should do upper ones to upper k, all right? It's a k-dimensional manifold. If I've got my coordinate chart, if I've got x here, then I can build that k-form there, right? That's what it means for it to be k-dimensional, is that that's a non-vanishing k-form. And I could prove that, I suppose. But if I've got another chart, let's say y, then from that I can build dy1 wedge dy2 wedge wedge dyk, you see? But for these to be consistently oriented, they need to be they need to be related in the natural way. And how are these related? Well, do you remember coordinate change? So like this is, the sum over I1 ik of, partial y1 partial x I1 partial yk partial x ik, and then you got yourself a dx I1 wedge wedge dx ik. All right? But that's the completely anti-symmetrized sum of the partial derivatives of y with respect to x. That's exactly the determinant of the partial y, let's say I, partial xj. It's this matrix, right? It's the determinant of that matrix times dx1 wedge wedge dxk. So to assume that these are positive is to assume that the top form built from the coordinate charts are pointing in some sense in the same direction. So like like here, this would be contrasting the one coordinate chart. Let me use this for the coordinate chart for a second. So like x1 would be the coordinate chart xyz here. Coordinate chart 2 here would be like yxz. So just using the same formulas but reordering them, switching an order will disorient your chart like that. Correspondingly, the top form built from the coordinate differentials won't agree. I mean, they never have to agree exactly. We're always allowing, there's a change of coordinates according to the determinant of the Jacobian matrix of the coordinate transformation. That's true. Of course, our the coordinate change chart for us is just linear, so its derivative is itself. It's stupid. But Jacobian matrix for these is like, I don't know. It's just got ones and zeros in it, I believe. So what I say then, going forward here, is, I guess I didn't quite finish my definition, did I? A manifold is orientable if we continue to travel across the manifold and we can choose coordinates such that on each overlap the transition functions satisfy that the determinant is positive. And I say, okay, so we also can say M is oriented if there exists a non-zero volume form on M. So if M is k-dimensional, then vol is simply a non-zero k-form. And so each point P, we can judge if a given coordinate system is left-handed or right-handed. So this is a different viewpoint. Another viewpoint is we're given outside of the, if you can imagine this, somehow outside of, or alongside perhaps, we have a k-dimensional manifold, and we're given two things. We're given a k-form, a non-vanishing k-form, which is called vol for volume, and then we're given a bunch of charts on the manifold. All right? Then we can judge whether or not those charts are left-handed or right-handed by seeing how they align with the vol or not. If that makes sense. Like, so definition, if M is k-dimensional and we're given vol, which is an element, it's a k-form on M, and it's it's non-zero, then you can judge like a chart X is consistently oriented if when we take vol and we feed it partial x1 partial xk, we get that is positive. That would be a positively oriented chart. And then, of course, if on the other hand, when you evaluate a coordinate system's partials on the volume, if you've got negative, then we'd say it's a left-handed coordinate system, right? So we can take the collection. If you have a non-vanishing volume form on the totality of your manifold, you can build a consistently oriented chart by just selecting all of the patches which give you positive like this, assuming that it's even possible. All right, there are manifolds where you cannot find an atlas of charts which covers everything and is consistently oriented on every overlap. Right, the standard example of this is the Mobius band, right? So if you take the Mobius band, which basically can just kind of imagine taking a strip, right, and twisting it, right, and then connecting these back around, right. I'm not very good at drawing it, but the the normal will be pointing out on this side, but then it's pointing in on that side. So if you try to join this point and that point, if you link them, you get the normal pointing in on this side, but the normal pointing out on that side. And the normal pointing in or out corresponds to it's the flux form. We can think about the flux form vector field correspondence, right? Like the normal vector field pointing, maybe the normal vector field pointing out would be like dx wedge dy, so to speak, over here. The normal vector field pointing in would be like dy bar wedge dx bar over there, something like that. If I'm saying I'm using like, if I have like x, y coordinates here, and then I have x bar, y bar coordinates over there, when then I look at where they overlap, I get the Jacobian's negative on the transition function between them, correspondent to the fact that you can't define a normal vector field on the Mobius strip all the way around, because you have to have a discontinuity where it goes back where it starts. But of course, if you would like to limit your scope to just a part, well, then all of a sudden you can do the integration. You just can't do it. I mean, I guess you could even do it on the whole thing if you make a choice as to what you're going. I mean, let me shut up. So I think you can make some ad hoc choices to still integrate on a Mobius band or something. But on the other hand, there's also an ad hoc choice with integration of a form, because you have to orient the manifold, and there are two choices. It's either positively oriented or negatively oriented. And what defines positive and negative is a matter of convention. For calculus 3, typically we take surfaces to be positively oriented to mean that the normal vector field is pointing in like the positive z direction, if that makes sense. Or if it's a closed surface, we insist that the orientation be pointed outside of the surface, right? Like away from the center. Okay. So, so I essentially have this calculation that I just went through in a little bit more detail on page 252 in some sense. All right. All right, so now on page 252, I'm also just writing down in detail what does the integral of a k-form look like if we choose one coordinate system versus another. All right? So why am I doing that? Maybe curiosity, you know?
Because we got different. Sorry.
Yeah, that's exactly that's what I'm looking at. Is like, what does the integral look like if we pull back with respect to one parameterization versus if we pull back with respect to a different parameterization, right? So let's see here. So I'm like, suppose you've got a k-form, alpha on the one hand, you can write it as h of x dx1 wedge da 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 wedge dxk, right? But we can also write it as I explain in the notes, and I can explain more here, as h composed with x composed with y inverse of y times the determinant of partial x partial y times dy1 wedge dy2 wedge dyk So let's see here, what's going on? So really all I've done is, this is essentially the calculation I was just sketching on the other board, right? That if you do the coordinate change for each coordinate, you have the completely anti-symmetrized wedge product, which brings out the determinant of the Jacobian matrix. So that's exactly what I'm writing here. I'm, converting, if you will, dx's to dy's. And when I do that, it brings out the partial x partial y matrix. And you notice here, I'm just composing it with y inverse composed with y. Anyway, the larger point is this is an element of the k-forms on the manifold, right? And so the picture is something like this. Here's your, let's say, what was my notation? V1, and then over here, I've got V2, right? So I've got some kind of overlap going on, and got some kind of overlap going on, right? And I have, what's the story here? I've got an x coordinate chart, I've got a y coordinate chart, right? So x, y, either way, you're going down to rk, right? And how do we define the integral? The integral of alpha over some region D, right? Well, it's equal to the integral of what? Basically x of D, right? And I'm gonna use the patch here, phi pull back alpha, right? And that literally is the integral, you know, the k-fold integration over that region of what? Of h of x, h of, how's it go? I have to replace x with what? With phi of x, of course. Oh, my bad. Well, fine. So here we get into the question of, do I want to use the same letter for the Cartesian variables as I do for the parameters? Like if I was to change to parameters, oh fine, let me shut up. So this, and then of course you got your dx1, dx2, dxk, right? But you could also calculate that as the integral, you know, k-fold integral of y of d, right? I guess it wouldn't be y of d, it would be, oh, it's not y of d, it's, let me think about this. If this is, so this is, down here is my x of d, and that maps over. I think I want to be looking at y inverse of x of d up here. Oh, yeah, I guess it's still x of d. Oh, man, I'm sorry. My brain broke. Just. Yeah, I feel like that should change.
So wouldn't y of d give you something? Wouldn't the y of d give you something not equal to?
Right, yeah, it should be, this one should basically, it's better if I use the other notation. You know, it's phi inverse. It's phi inverse of d, whereas this would be psi inverse of d. All right, the d is up here. So so this is phi, and the inverse of y is psi in my notes here.
Is the intersection or the whole thing?
The intersection of v1 and v2.
Oh.
So that we have both charts making sense here. And so this one, so when I write my k-form in the y coordinate chart, right, like this, then by definition the integral of this is literally h of, I think psi, it works out to psi of y, you know, the determinant of this guy, and then you got your dy1 dyk. And I think I'm supposed to put, well, no, it's just that. It is just that. And so you might wonder, so I guess I wrote, in the notes I wrote it as h composed of x composed of y inverse of y. Fine. I should write this as h of, goodness gracious, it's right here, of, I'll get it eventually, h composed with x composed with y inverse of y. That's just a fancy way of saying take the formula for h and rewrite it in terms of the y coordinate. It's making a substitution. So the point of all this is, if I'm going to calculate a k-form's integral, right, according to the definition I introduced last time, I'm going to have an issue with the calculation being coordinate dependent if I'm not careful. See, because this is just a calculation we just did. And in multivariate calculus, there's a there's a multivariate integration change of variables theorem. What does the theorem for multivariate calculus say? It says that this is equal to the integral, da da da. You change the bounds in terms of the other variable, you substitute the other variable just like we got. All right? Make the substitution like I've indicated here. Fine. All right, make our substitution for our integrand. We multiply, but here's the rub. We multiply by the absolute value of the Jacobian. Remember, there's an absolute value of the Jacobian determinant. Remember that? There's an absolute value there. So, think about this. If your manifold's not consistently oriented, you run into ambiguities here. See, because on the one hand, you could just change coordinates for the integral in RK and have to have the absolute value there. On the flip side of things, if you take your form up on the manifold, choose the y coordinates, which are left-handed, whereas your x's are right-handed, then this gives you minus what that is. So your integration theory becomes unstable if you don't use consistently oriented charts. That make sense? That's why it matters. Because we're up against the change of variables theorem, and we have to be consistent with it. In order to be consistent with it, we must choose one K-form to bind them all. Or you got to be sneaky and do something that I don't know how to do on a Mobius band, but I've heard about it. All right, so there's that. I guess I still haven't really explained how we, how do we get the boundary? How do you get the, the positively oriented boundary? How do we define that? So going forward in my notes, like the next thing I do is derive the line integral from the pullback of a 1 form, and then I do the the deflux form is the pullback of the 2 form on page 254, which is what I started class with. All right. Let's see here. So I would say at this point, pretty much we've done. And then I have some just like some snazzy formulas for the how do you actually, what's the formula actually look like in practice? Like what's the parametric formulas for a so some of these formulas date back to the first time I taught this material, which was as a grad student. When I was a grad student, I taught a course called Math Models in Physics that was basically this stuff. And there I wrote this formula. If we're integrating a K-form gamma, rather a P-form gamma over a P-dimensional volume, all right, then what you do is you integrate the P-dimensional integral over the parameter space, right? And the way it goes is gamma I1 I2 da 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 IP, which I guess I should clarify. That means what? Well, this is that component function evaluated at the parameterization. All right. There's P parameters. All right. And then you contract that against partial x I1 partial U1 partial x I2 partial U2 da 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 partial x